Why is chemical potential important for multi-component systems? Imagine you're mixing different drinks at a bar. Each ingredient wants to find its perfect spot, balancing energy and flavor. That's where chemical potential comes into play. It's like a measure of how eager each component is to move, react, or change within a system. When you have more than one substance, understanding how they behave together becomes more complex. Chemical potential helps us see how each part influences the whole. Think of chemical potential as the driving force behind how substances distribute themselves. If one component has a high chemical potential, it tends to move or react to lower its energy. This movement is spontaneous because it increases the system's overall entropy or disorder. When systems change naturally, they tend to move toward states of lower free energy, which is a combination of energy and entropy. That's why chemical potential is linked to spontaneity. In multi-component systems, each substance has its own chemical potential. These values tell us where each component prefers to be. For example, in a solution, substances will spread out or react in ways that lower their chemical potentials. This process continues until all components reach a balance point called equilibrium. At this point, the chemical potentials of each component are balanced in a way that no further net change occurs. Understanding chemical potential is key to predicting how systems behave when they are not in equilibrium. If the chemical potential difference between two parts of a system is high, the system will tend to change to reduce that difference. This is how diffusion works, where particles move from high to low chemical potential areas. It also explains why reactions happen spontaneously when they decrease the total free energy of the system. Chemical potential also connects to the idea of irreversibility. When a process occurs in a way that lowers the total free energy, it is irreversible. Once the system reaches equilibrium, no further spontaneous change occurs unless external energy is added. This is because the chemical potentials have balanced out and the system is in a stable state. In practical terms, knowing the chemical potential helps us control processes like chemical reactions, phase changes, or even how nutrients move in biological systems. For example, in batteries, the difference in chemical potential between electrodes drives electrons, creating electrical energy. In biological systems, chemical potential differences control how nutrients are transported and how energy is produced. So, in essence, chemical potential is a vital concept for understanding how multiple substances interact, move, and reach balance. It tells us which way processes will go, how systems will change, and when they will settle into a stable state. It links energy, disorder, and equilibrium in a way that helps us predict and manage the behavior of complex systems.